Welcome back. In this lecture, we will discuss about the solution of variable coefficient differential equations. We have seen that if the differential equation is constant coefficient, whether it is a first order, second order, third order, then the method of solution we have already seen in the previous lectures, that you find the characteristic equation, solve, after solving or finding the roots, we formulate the solution and we get the general solution and particular solution. And in case if the differential equation is having a variable coefficient, then that method fails. For example, if I consider a general differential equation, say a second order. So, consider a second order variable coefficient differential equation. Say this is a0x y double prime plus a1x y prime plus a2x y is equal to 0. So, call this equation as 1. Then how to solve it? By the method of characteristic equations and finding the roots will not work. But there are certain situations where special forms of this equation which can be solved just as how we did in a constant coefficient differential equation. So, for example, if we can reduce this variable coefficient differential equation into a constant coefficient differential equation by giving some suitable transformation. For example, if we consider, so example, so consider the Euler-Cauchy equation. So, Euler-Cauchy equation, so given by x square y double prime plus axy prime plus by is equal to 0. So, where a and b are constants. So, this equation, though it is a variable coefficient, it is in a nice form. This can be reduced into a constant coefficient differential equation just by applying some transformation. So, consider the transformation. Consider the transformation. Say z is equal to natural logarithm of x, or x is equal to e to the power z. So, if you use this transformation, then we are changing the independent variable from x to z. So, if you do this transformation, then what is dy by dx? Dy by dx is given by the chain rule dy by dz into dz by dx, which is equal to, by using the transformation, 1 by x, dz by dx is z is ln x. So, dz by dx is 1 by x dy by dz. So, therefore, differentiating a function with respect to x is equivalent to multiplying 1 by x and taking the derivative of the function with respect to z. That becomes the rule. So, if for this a case, then if we find the second derivative, so d square y by dx square is nothing but d by dx of dy by dx. So, we apply the rule stated just above, that is differentiating a function with respect to x is equivalent to 1 by x into differentiating the function with respect to z. So, therefore, we get the second derivative d square y by dx square is equal to d by dx of dy by dx, which is equal to 1 by x times d by dz of dy by dx. So, which is again by definition 1 by x times d by dz of, what is dy by dx? dy by dx is 1 by x, again 1 by x dy by dz. So, which is equal to 1 by x times d by dz of 1 by x is by transformation e to the power minus z. So, dy by dz, and now we can differentiate with respect to z. So, this gives me 1 by x into minus e to the power minus z. So, applying the product rule, dy by dz plus e to the power minus z times d square y by dz square. So, this is equal to, and this e to the power minus z, e to the power minus z is 1 by x, and this is also 1 by x, can take 1 by x outside. So, this gives me 1 by x square into minus dy by dz plus d square y by dz square. So, therefore, the second derivative d square y by d square y by dx square is 1 by x square into minus dy by dz plus d square y by dz square. So, this implies that x square into d square y by dx square is equal to minus dy dz plus d square y by dz square. Now, putting this into the Euler-Cauchy equation. So, therefore, the Euler-Cauchy equation becomes minus dy dz plus d square y dz square plus a times dy by dz plus by is equal to 0. And therefore, if you simplifying this and taking d square y by dz square first. So, this is d square y by dz square plus a minus 1 dy by dz plus by is equal to 0. So, look at this equation. This equation is a second order constant coefficient differential equation. So, we started with the Euler-Cauchy variable coefficient differential equation. The transformation reduced this into a constant coefficient differential equation, of course, is second order, and this equation can be solved. Now, we are taking the characteristic root. So, it is a constant coefficient differential equation. So, this is a constant coefficient differential equation so the method is characteristic roots, find the characteristic roots, and these three situations where the roots are real and distinct, the roots are real and equal, and roots are complex. So, which we have already seen. So, for example, if we take the characteristic roots, the roots are given by lambda 1, lambda 2 is equal to 1 minus a plus or minus square root of a minus 1 the whole square minus 4b all divided by 2. So, the discriminant of the equation b square minus 4ac by 2. So, case if if the roots are real, roots are real and distinct. So, call it then lambda 1 lambda 2 are the real roots. Then the solution is given by y of, remember the independent variable is now changed to z, y of z is given by c1 e to the power lambda 1 z plus c2 e to the power lambda 2 z. And again, so if I want to change it back in terms of x to change the independent variable back to x, use a transformation. So, therefore, y of x is equal to, you change z to x, that is c1 e to the power lambda 1 and z is ln of x. So, ln of x plus c2 e to the power lambda 2 ln of x, and this is nothing but ln of e to the power lambda 1 ln of x is, so c1 if you simplify it is x to the power lambda 1 plus c2 x to the power lambda 2. So, this is a general solution. So, general solution. If the roots are real and distinct, and similarly if the roots are real and repeated and the roots are complex, can be treated similarly. Okay, this is a situation where if the differential equation is having a very special form, and in case now we are going to deal with differential equation which is in a general form, that is a0x y double prime plus a1x y prime plus a2x y is equal to 0. Or if this cannot be reduced into a constant coefficient equation and no other methods are available to solve it, then one method of solving is by using the power series solution, the series solution of this differential equation. So, let us see how to solve this by using a power series solution. So, power series solution. To the equation a0 x y double prime plus a1x y prime plus a2 x y is equal to 0. And what we expect is, we expect a solution we expect a solution to this equation, call it 1 in the form y of x is equal to summation n goes from 0 to infinity c n x minus x 0 to the power n, where c 0, c 1, c 2 etc. are constants. So, we expect a solution to the variable coefficient differential equation 1 in a power series form, in infinite power series about a point x 0. Now, the question is does there exist a power series solution? Does there exist a power series solution to 1 in the form 2. So, call this form as 2. So, does there exist a power series solution to the above differential equation in the form 2? And if it exists, how to compute the constants c 0, c 1, c 2. So, if s, how to compute c 0, c 1, c 2 etc. in 2. So, these are the two questions. So, first we address the existence of power series solution to one. So, under what condition the power series solution for 1 exists and that series is convergent. To answer this question, we need some of the basics ideas, some basic definitions. So, to address the existence problem, that is under what condition one has a power series solution of the form 2. So, we require some conditions and we define, and let us again state the form of the equation a0x y double prime plus a1x y prime plus a2x y is equal to 0, and equivalent normal form is So, we call this equation 1, and if we take the equivalent normal form y double prime plus p1x prime plus p2x y is equal to 0, where divide throughout by a0. So, where p1x is equal to a1x by a0x and p2x is a2x by a0x. So, now we define what do you mean by a analytic function. Definition: a function a function f is said to be analytic, a real valued function f is said to be analytic at a point x 0 if its Taylor series expansion, about x 0 given by summation n goes from 0 to infinity, the nth derivative of f evaluated at x 0 divided by n factorial into x minus x 0 to the power n. The Taylor series about x 0 exists and converges to f x for all x in some neighborhood of x 0 containing x 0. So, neighborhood in some neighborhood, or in this case is interval, some interval containing x 0. So, in this case we say that a function is analytic. Examples see, all polynomial functions are analytic, all polynomial function are analytic everywhere. And the functions containing e to the power x, sin x, cosine x, they are also analytic. And another important class of functions analytic is all rational functions. So, rational functions of the form p x by q x, where p x is a polynomial, q x is a polynomial. So, rational functions are also analytic at all points except the denominator, the points at which the denominator is not 0, except at the point the denominator is equal to 0. So, rational functions is analytic except those values of x at which the denominator is 0. For example, if we take a rational function 1 by x square minus 3x plus 2, which is written in the form x minus 1 into x minus 2. So, this is analytic at all points except at x is equal to 1 and x is equal to 2. At these 2 points, x is equal to 1 and x is equal to 2, the rational function is not analytic, elsewhere it is analytic. Now, a point is okay, another definition is ordinary point for a differential equation. So, definition the point x 0 is called an ordinary point is called an ordinary point of the differential equation. Okay, 1 if differential equation 1 is in the normalized form, so call it y double prime plus p1x y prime plus p2x y is equal to 0. If both functions, if both of the functions p1x and p2x are analytic at x0. A point x0 is said to be an ordinary point of the differential equation in the normal form y double prime plus p1 x y prime plus p2 x y if both of the functions p1x and p2x are analytic at x0. If that fails, if it is not true, then we say the point is a singular point. A singular point if either or both of these functions are not analytic at x0, then x0 is called a singular point. A singular point of the differential equation. See quickly, let us look into an example. Y double prime plus x y prime plus x square plus 2y is equal to 0. So, here p1x is just x and p2x is x square plus 2. So, obviously both are analytic for all points are ordinary point. For this differential equation, all points are ordinary points. And if we consider another differential equation, x minus 1 y double prime plus x y prime plus 1 upon x y is equal to 0. So, here p1x is x upon x minus 1 and p2x is 1 by x into x minus 1. So, p1 is analytic for all points except at 1. Okay. So, for p1 x is equal to 1 is a point at which p1 is not analytic, and here x is equal to 0 and x is equal to 1 for p2 is not analytic at these 2 points. So, therefore, the differential equation is analytic for all points except 1 and 0. So, the conclusion is 0 and 1 are the only singular points. So, this tells us x is equal to 0 and x is equal to 1 are singular points. Points of the differential equation. Now, if x0 is an ordinary point of a differential equation, then we have a sufficient condition to guarantee a power series solution. So, now I state the form of a theorem. Theorem says if x0 is an ordinary point, is an ordinary point of the differential equation, call it y double prime plus p1x y prime plus p2x y is equal to 0. Then it has two linearly independent non-trivial it has non-trivial two linearly independent power series solution, of the form yx is equal to summation Cn x minus x0 to the power n, n goes from 0 to infinity, and the series converges in some interval, the interval of convergence x minus x0 less than some r. So, this is an important theorem, guarantees the existence of a power series solution to a differential equation. If x0 is an ordinary point of a differential equation, then about that point we can find, if you have a second order equation, then we can find two linearly independent power series solution. So, existence of two linearly independent power series solution at an ordinary point is guaranteed by this theorem. So, now the method of solution, how to compute the solution. So, method of solution is by method of solution, what do we want to find? We want to find C0, C1, C2 etc., all these coefficients in the expression y is equal to, our series solution is of the form C0 plus C1 x minus x0 plus C2 x minus x0 square plus etc., which is in compact form we write as Cn x minus x0 to the power n, n goes from 0 to infinity. So, our aim is to find these coefficients. Our aim is to find these coefficients. Okay, so since the series converges since the series converges on x minus x 0 less than r, some number r, by the existence theorem, since the series converges for x minus x 0 is less than r about the ordinary point x 0, okay, the series can be differentiated term by term. It may be differentiated term by term on this interval. See, dy by dx is derivative of y, which is c1 plus 2c2 x minus x 0 plus 3c3 x minus x 0 square plus etc., which is summation n goes from 1 to infinity n cn x minus x 0 to the power n minus 1. And similarly, the second derivative d square y by dx square, the derivative of the above series, which is 2c2 plus 6c3 into x minus x 0 plus 12c4 into x minus x 0 square plus etc., which is written as summation n is equal to 2 to infinity n into n minus 1 into Cn x minus x 0 to the power n minus 2. So, now substituting these values of y dy by dx, d square y by dx square in the original equation, now substituting y dy by dx, d square y by dx square in the differential equation, okay, and simplifying we get some constant k 0 plus k 1 into x minus x 0 plus k 2 into x minus x 0 square plus etc. is equal to 0, where these constants k 0, k 1, k 2, these are functions of our other constants c 1, c 2, etc. So, since the series, it is valid for all x in the interval x minus x 0 less than r, that is interval of convergence. And now equating right hand side and left hand side, the coefficients of x, x square, x cube, etc., and also the constant terms, we get k 0 is equal to 0, k 1 is equal to 0, k K2 is equal to 0, etc. So, we get equations K0 is equal to 0, K1 0, K2 0. If we solve these equations, then we get the values of C0. So, solve these to obtain values of C0, C1, C2, etc. And once we have C0, C1, C2, etc., plug in into the series form, we get the series solution. The series solution Yx is equal to summation Cn x minus x0 to the power n. So, this is the method. So, let us illustrate this by an example. So, let us consider an example. So, what is the problem? The problem is, the question is to find the power series from the power series solution of the differential equation find the power series solution of the differential equation given by y double prime plus x y prime plus x square plus 2 y is equal to 0. So, find the power series solution of the differential equation in powers of. So, the question is to expand or get the power series solution in powers of x. So, that is you are asked to expand get the solution in powers of x minus x0, where x0 is 0. Let us check whether 0 is an ordinary point. Okay. So, obviously, your P1 is x, P2 is x square plus 2. So, all points are ordinary points. So, all points are ordinary points. So, x0 is equal to 0 is an ordinary point. So, therefore, by the existence theorem, there exists a power series solution. So, two linearly independent power series solution of the form summation Cn x to the power n. So, we look for a solution Yx, y is equal to summation Cn x to the power n, n goes from 0 to infinity. So, this is guaranteed by the existence theorem. So, there are two linearly independent power series solution. So, we want to now our aim is to find this C0, C1, C2, Cn. So, what we do is by differentiating we get y prime. Y prime is summation n goes from 1 to infinity n into Cn x to the power n minus 1, and similarly y double prime is summation is going from n is equal to 2 to infinity n into n minus 1 x to the power n minus 2. Now, plug in these values to the given differential equation. So, substituting in the differential equation, we get summation n into n minus 1 C n x to the power n minus 2, the first term, that n goes from 2 to infinity, n goes from 2 to infinity, the first term, and the second term is x into y prime, which is x into summation n goes from 1 to infinity n into C n x to the power n minus 1. Now, the third term is a sum of two terms, x square plus 2. I take x square into summation into y, summation C n x to the power n, n goes from 0 to infinity, plus constant term 2, 2 into summation n goes from 0 to infinity C n x to the power n, which is equal to 0. Since x is independent of the index, we may rewrite this. So, rewriting we get summation n goes from 2 to infinity n into n minus 1 C n x to the power n minus 2, the first term, plus summation n is equal to 1 to infinity n into C n x to the power n, plus summation, if we have just multiplied each term by x, you get x to the power n, and n goes from 0 to infinity, the third term, there also we did a multiplication by x square. So, that results C n into x to the power n plus 2 when multiplied by x square, plus 2 times summation n goes from 0 to infinity C n x n is equal to 0. Now, look at the first and third term, this first term and the third term. The first term, the index is n minus 2, the third term the index is n plus 2. We want to make all the same uniform index, that x n. So, we can do the following to rearrange that. So, consider the first term. So, consider the first summation, and replace n minus 2 by a new variable, new dummy index m. So, therefore, what we have is m is equal to n minus 2 or n is equal to m plus 2. So, if you use this, then the summation becomes, then this gives the first term in terms of m. M goes from 0 to infinity. Now, n is going from 2 to infinity, that becomes, when n is 2, m is, when n is 2, m is 0. So, the summation goes from 0 to infinity m plus 2 into m plus 1. So, n becomes m plus 2 and n minus 1 is n plus 1 into C m plus 2 into x to the power m. Now, remember that m is just a dummy variable, m is a dummy variable, dummy index. We can change m to n, change m to n notation. So, therefore, it becomes summation n is equal to 0 to infinity n plus 2 into n plus 1 into C n plus 2 x to the power n. And similarly, if you do the same thing for the third term, third term. So, similarly, the third term, that will make n plus 2 is equal to m, or n is m minus 2. So, this gives in terms of m, this will be m is going from 2 to infinity, instead of n is going from 0 to infinity, and m is going from 2 to infinity, c m minus 2 and x to the power m, and again that is m is a dummy index. So, therefore, we can plug back the n, or okay, this is n goes from 2 to infinity, c n minus 2 x to the power n. Okay, so, now the index of all these terms are n with respect to n. Okay, so, what we do is the equation now becomes the equation becomes summation n goes from 0 to infinity n plus 2 into n plus 1 c n plus 2 x to the power n plus summation n goes from 1 to infinity n c n, there we did not do any change, x n, plus summation, the third term term is also changed, n goes from 2 to infinity c n minus 2 x n, plus the last term 2 times summation n goes from 0 to infinity c n x to the power n is equal to 0. Now, we want to make some common range. Since the summation is not uniform, one is starting from 2 to infinity, another one is 1 to infinity, other one is 0 to infinity. The common summation range is 2 to infinity. So, the other terms we can separate out. For example, the first term, summation, the case n is equal to 0 and n is equal to 1 can be separated out. So, therefore, what we get is this term, which is 2 c 1 2 times when n is equal to 0, get 2 c 2 plus 6 c 3 x plus the common range n is equal to 2 to infinity n plus 2 into n plus 1 into c n plus 2 into x to the power n. And similarly, for the second term, that can be split as c 1 x plus the common range n is equal to 2 to infinity n c n x to the power n. And third term we do not have to change. The last term we can change, this is 2 c 0 plus 2 c 1 x plus summation c n x to the power n, n goes from 2 to infinity. Now, if we rearrange all this, we get, this implies that 2 c 2 plus 6 c 3 plus a summation the first term. Okay, so if we combine all these things together, if we add them together, we get 2C0 plus 2C2 plus 3C1 plus 6C3 x plus summation, the common summation we take, n is equal to 2 to infinity n plus 2 into n plus 1 C n plus 2 plus n plus 2 C n plus C n minus 2 times x to the power n is equal to 0. And this series converges for in the interval x minus x 0 is less than r. So, equating the coefficients of the powers left hand side, okay, to 0, because right hand side is already 0, we get 2 C 0 plus 2 C 2 is 0 and 3 C 1 plus 6 C 3 is 0, and this gives C 2 is minus C 0 and C 3 is minus half C 1. And also we get from the summation term that n plus 2 into n plus 1 C n plus 2 is equal to is plus n plus 2 into C n plus C n minus 2 is equal to 0. If we solve it, C n plus 2 is obtained as minus n plus 2 C n plus C n minus 2 divided by n plus 1 into n plus 2 for n greater than 2. So, therefore, for each case n is equal to 2 case, C 4 can be solved. C 4 is minus 4 C 2 plus C 0 by 12. So, this implies that C 4 is 1 by 4 C 0. And similarly, n is equal to 3 case, C 5 is solved to be 3 by 40 C 1. So, therefore, the solution can be written as by using these coefficients. So, y of x is equal to C 0 into 1 minus x square plus 1 by 4 x to the power 4 minus etc. plus C 1 into x minus half x cube plus 3 by 40 x to the power 5 plus etc. So, we see that there are two series. So, this is two series solutions, the first one and the second one. They are linearly independent two series solutions, and their linear combination C 0 of the first one plus C 1 of the second one is a general solution. It's a general series solution. So, therefore, by doing this method, we can find if a point is a ordinary point, we can get the series solution and two linearly independent series solution of a differential equation if the point is an ordinary point. And if the point is a singular point, there are methods, Frobenius methods and all that will come in another series. Okay, so with this I would like to finish. So, we have seen even if the differential equation is variable coefficient, we can have a solution in power series form, series solution. Okay.